The bootcamp, and we'll have the pleasure of listening to Susanna de Rezende. We'll start talking about proofs, circuits, and total search problems. Please, Susanna.
Okay, so yeah, just please feel free to interrupt at any moment. And tell me if I'm going too fast or too slow. Okay, so one of the motivations, I could say, to talk about this topic is that there have been many papers coming out lately. I even didn't update this with the ones these last year, which really have these total search problems at the center. And there are some new connections between these two different worlds, and they're actually new but extending like classical ones. So both viewing proof and query complexity as one of the worlds and circuit and communication complexity as the other. And the newer connection would be in one of these directions, even though it dates back. So, and this is like part of a bigger theory, which I will touch upon at the end, but I will mostly stick to more classical relations during the talk. So the plan is as follows. I'll try to introduce these two more classical connections, and at least to give some intuition of where they come from. So the tree-like resolution and decision trees, monotone Boolean formulas and communication protocols, and then try to explain where these total search problems come, why are they central, and then explain how these two worlds are connected, which we already saw a feasible interpolation in Tony's talk, and then lifting theorems, which go in the other direction. And then finally, I'll end up with just some recent results that have used this point of view and some open problems. Okay. So, and there's more on this. There's a complexity guess column, which is kind of a short, high-level survey on some of the things I'll touch upon. Robert has a talk online, which also has a lot of this, and there are many recent papers on TFNP, which I recommend. Okay, so tree-like resolution and decision trees. So here the total search problem we'll be focusing on is this. Tony already mentioned this falsified clause search problem. So here we're given an unsatisfiable CNF formula. Here I have M clauses, and the goal is to find some clause which is falsified by the given assignment. So it's total because it's unsat, right? And I'll just view this as a relation. And I have a X here and kind of overloading notation for the variables in the assignment, but I would say a pair Xi is in this relation if the assignment X falsifies clause I. And this is exactly the search problem. Okay. In general, total search problems they have some input and some output. For now, we can think of the input as just 0, 1 to the n. And I'll write, so S of X is all the possible feasible outputs given the input X. And it's total if for all X in the input, there is at least one possible feasible output. And yeah, as I mentioned, the search F is a total search problem if F is unsat, if and only if F is unsat. Okay, so this is what we would like to compare: the query complexity of this problem with the proof complexity of refuting F. Okay, so we already saw resolution proofs. So just to mention, I'll be considering for now tree-like resolution proofs. I'll use a rough estimate for size, so it's just the number of nodes in the DAG. I won't really look at the size of each clause. And I'll be talking. Yes, I will. Next slide. I will. And yeah, I'll use the notion of depth of the proof, the longest path from the source to the sink, and the notion of width, which is the maximum number of literals in any clause appearing in the proof. So these are the measures I'll use. So query complexity. So here we have a decision tree that is solving this falsified clause search problem. So the query complexity will just be the depth of this tree. And so it's querying variables, and at the end it has to output a falsified clause. So the classical result here is that tree-like resolution refutation of a formula F is equivalent to the decision tree complexity of the falsified clause search problem. Okay, so here we have two examples which actually look very much alike, but let's see why. These are essentially the same object. So first, yeah, I'll do just one direction. But suppose we're given a tree-like resolution refutation, and now we have to come up with a decision tree that solves the falsified clause search problem. So what we'll do is we'll look at what is the variable I'm resolving on at each step. That will be the variable I'm querying. And the invariant I'll keep is that the assignment so far is going to falsify the corresponding clause. So at the beginning, I have the empty assignment, and it falsifies the empty clause, so I'm fine. The first variable that I'm resolving on, in this case, it's x1. So that's going to be the variable I query. And now I have to consider, well, with it's true, then x1 being true falsifies the clause not x1. So I'm keeping the invariant. And now I look at what is the next variable I resolve on. And well, that's x2. And now I'll consider true and false according to what falsifies the clauses there. So again, I'm keeping the invariant and so on. So as you can see, I get exactly the same structure. So not only is it the case that, yeah, size S that the tree-like resolution refutation implies size S that the decision tree, but I actually get a same structure. And also in the other direction, I can also do this. Okay. Any questions here? So now, right. So what is the query complexity of total search problem? So now this would correspond to what is polynomial time. So we have the total search problem, and so the query complexity of it would be the depth of the shallowest decision tree that solves this problem. And I'll call this FPDT all the total search problems that can be solved with depth polylog n. Okay, so this is what corresponds to the polynomial time in the total search problems. So let's see some examples. For example, if I have the problem, I'm given a graph which is not too colorable, and the problem is to find some, and I'm give a coloring of it, and the question is, can I find a monochromatic edge of G? So this problem is in this class, and why? Well, if the graph is not too colorable, it has some odd cycle, I can just do a binary search in the odd cycle and find a edge which is monochromatic. Another example would be unsat 2CNF formula. There's a similar argument where I find a cycle and do a binary search. So these are some problems that are in FPDT. Okay, so what is the NP correspondence here? So here we'll define the notion of certificate. So a certificate is just a partial assignment, and such that there is some output for which all assignments that are consistent with this partial assignment have this output as a possible answer. So so this would be a possible certificate, and I would like a set of certificates that actually covers all inputs, so that there is one certificate in the class that is consistent with, so for every X there exists one certificate which is consistent with. And once I have a certificate cover of S, then I can come up with an NP algorithm that solves this search problem. And it's simply, well, I just guess the certificate, and now I just need to query in my input just what my certificate, what are the variables that it fixes. So I query that and check whether X is consistent with that. So the complexity of this NP algorithm would be the maximum size of any of the number of fixed coordinates in any certificate in my certificate cover. So this will be the notion of complexity here for this algorithm. So now I can also define similarly, so this class TFNP dt of S would just be the minimum over all certificate covers of this measure. And this whole class TFNP dt would be all total search problems that have a measure of polylog n. Does this make sense?
Can you repeat, what are you trying to define as correspondence?
This is supposed to be the NP version for total search problems. So I'm trying to define what would be a certificate, and I would like to cover all possible inputs. Since it's a total search problem, there should be a certificate for all inputs.
And what was the DT superscript?
Oh, the DT is decision tree. Sorry. Yes. Yes, because I'm talking about this. So here in this model, I'm querying. The number of queries would be the depth of the decision tree. So there's a non-deterministic part where I guess, but then I query the part of my certificate that's fixed and query and X those positions and check that it's consistent with my certificate.
So in this world, like all CNF formulas of the most polylogarithmic width, they're like NP easy because I just guess a falsified clause and check that it's falsified. But the deterministic like decision tree complexity could be way larger.
Yes. Yeah, exactly.
We can separate PL and PL in this world.
Yes. Yes.
Is there a way to characterize it in terms of FP? That we know what we do in classical complex world is one FP in terms of P. Right? So here we wanted to find P of FP in terms of FP.
You would just choose.
Yeah, the certificate is the decision tree.
Yeah. Exactly. So yeah, there exists for every input there exists a decision tree. So if you would guess that one. Okay. Yeah. So let's see go back to search app. So this is what Jakob was saying. So if we have an unsatisfiable CNF formula, the clauses are a certificate cover for the falsified clause search problem. So I know that the complexity, the TFNP dt complexity of search F is not more than the width of this formula.
What is the width of the formula?
Oh, the number of literals in the maximum number of letters in any clause appearing in the formula. Yeah, so that's exactly what I would have to query to make sure that my assignment falsifies the clause. And the reason this problem, falsified clause search problem, is so important is that it is complete in some sense, because if I have, so suppose I have any search problem S, and consider, well, any certificate cover, maybe the best one possible, then I can reduce it to some search F for some formula F. And the formula I choose is simply I look at all the certificates in the certificate cover, and I define the clause that is exactly falsified by this certificate. So it's the maximum width clause falsified by this certificate. And now if I solve the search problem for this formula and I find a falsified clause, I will be finding a certificate in R for the assignment. And also conversely, if I find a certificate in R, then I can find a falsified clause. So it is complete in this sense. Okay, so we have a similar parallel in the monotone circuit and communication protocols world. So you'll kind of see the same structure I'll go over again, but now in this world. Okay, so I think I'll go over this, but I think most of you have know this very well. We have the Karchmer-Wigderson game. So we have a Boolean function f. Here it can be a partial Boolean function. So there's this total search problem, which is the Karchmer-Wigderson game on f. I'm given x in the preimage of 1, y in preimage of 0. So these inputs have to be different. And the goal is to find some index where they differ. And this is a total search problem. Now my input is actually not just 0, 1 to the n, but is this cross product. And so let's just see some examples. So if f is parity and I have these two inputs, then the only possible output I can give is 4. It's the only place where they differ. Here I have two inputs that differ in 3 positions. So yeah, there are 3 possible answers here. Okay. We have this notion of the Karchmer-Wigderson game, and there's a monotone version of it. So if f is monotone, then the monotone Karchmer-Wigderson game of f is actually a harder problem, because I'm asked to find an I where xi is 1 and yi is 0. And since it's monotone, this has to exist by the definition of monotonicity. So let's go back to the example for majority. So here, this possibility here with xy3 would not be an answer for the monotone version, even though it's an answer for the non-monotone version. So it is a strictly harder problem. And now what Karchmer-Wigderson showed was that the communication complexity, which I'll define now, of this Karchmer-Wigderson game of f is exactly the circuit complexity of f, and also in the monotone world. So this is just to say I'll be considering De Morgan Boolean circuits. So I just have OR and AND gates, and I have variables or negated variables as inputs. And yeah, I'll just be considering.
Go back to the previous slide.
Yes.
Don't you need the log of the monotone circuit?
Yeah, so I'll define what these complexities mean. So in order, it'll be depth in both cases. Or yeah, what I'll talk about now is the depth in both cases. Yeah, but there's also a similar for size in both cases. Okay, so the communication protocol. So we have these 2 players, Alice and Bob. Alice has the input in the preimage of 1, Bob in the preimage of 0, and their goal is to find an index where their inputs differ. And their communication protocol is this strategy tree that defines who speaks, and at the end they should output what is which of their what is the index of their bits that differ. Yeah, and these are the 2 complexity measures I'll talk about here too. So this probably looks familiar. So let's see how from now a formula, I can get a communication protocol that solves the Karchmer-Wigderson game. Okay, so I have and OR gates. So what I'll do is every AND gate will be Bob that speaks. Every OR gate is Alice. And the invariant we'll keep is that if we consider the partial function computed at a given gate, Bob's input will be in the preimage of 0 of that gate. Alice's input will be in the preimage of 1 of that gate as they walk down the tree. So this is true at the beginning because we're guaranteed that that's the input that they get. And now we just have to make sure that they can follow this until the end, because then the end is just literal. So then they'll have a different function. And if it's monotone, Bob will have a 0 and Alice will have a 1, which is exactly what they have to find. Okay, so Bob he'll start speaking and he has to say which direction to go. And those in the OR gates, Alice will speak and she will say what direction she has to go. So let's consider an input. So Alice has, suppose she has 1, 0, 0. Bob has 0, 1, 0. And now just to make sure that Alice has something in the preimage of 1, if we compute this formula here, we'll see that Alice gets a 1. And if we compute it for Bob, you can see that Bob gets a 0. Okay, so this is a valid input. And now let's see what Bob and Alice would do. So Bob, since he gets a 0, he has to go to the gate where his function is still 0. So what he'll do if he had this input would say, well, I have to go to this gate. And then now once here, Alice has a 1. She has to have a 1 because that was an AND. So she has to have 1 in both directions. And now she can say, since this is an OR gate, she can say which of these two she has a 1. She has to have 1 in at least one, and Bob has to have 0 in both. So that would be a valid one. That makes sense? Okay, and similarly as we had before, the converse also holds. So this again is really, you really get the same object. The graph structure is the same when we do this translation. So in the communication complexity world, we also have these total search problems. And now I'm defining FPCC because we're in the communication world. And the complexity will be the depth of the shallowest protocol that solves the total search problem. And we have the input divided between the two players. And again, the polynomial time version of this will just be all search problems that have communication protocol trees of depth polylog n. And now the NP communication complexity of these total search problems, again, we'll have certificates, but now the certificates, they look like rectangles of some subset of Alice's input, a subset of Bob's input, such that there is some answer which is common to all inputs in here. So this is a certificate, and again, we want a set of certificates that cover all inputs. So it looks something like this. It's a set of rectangles that cover all inputs. So given this, we can again define our NP algorithm, which solves the search problem. So now Alice is getting some X, Bob is getting some Y, and now they both have to non-deterministically guess what rectangle they're in. They can independently check that they're actually in that rectangle, but now they have to communicate log number of rectangles bits to make sure that they both have the same rectangle. So the complexity solving some search problem, I would look at the smallest possible rectangle cover of S, and that would be the log of the number of rectangles. And again, the TFNP class would consist of all the total search problems that have complexity polylog n. Yes.
So when you define the complexity, you said depth of the shell of this protocol, you just meant number of bits sent, right?
Number of bits sent, yes.
Because I thought it rounds, but then it's always one. You just send the input to the other person.
Oh yeah. No, it's number of bits sent. So I'm just viewing the tree and considering the depth of the tree. And the reason for this is we'll get to soon, because you can also consider size. So that's what I'll get to soon. Any other questions?
Is there a reason why you're considering polylog n as opposed to just like O of log n or something?
Yeah, that's a good question. Like I'd say the reason is you need at least log n. So that would be just because you have n possible answers for most of these settings. So you need your tree has to have at least that log n. And so yeah, the natural measure that comes out is this. I don't know. Maybe Robert has a better answer.
Well, anything can be done in complexity n. So if that's the analogy of like exponential time, like 2 to the n, like if we're taking a everything is scaled down by a logarithm. So like polylog is kind of the more natural way of saying it.
Think of it as an oracle. So like the
Yeah.
strings that they have are like oracles. And so the input size is log n.
Okay.
And therefore
Okay.
log n is no longer enough.
Okay.
Yeah, sometimes when they describe TFNP, they actually have this scaling. So the input is actually of exponential size, and then they say poly n here.
This makes
But,
sense.
yeah. Okay, and again, now we also have some sort of completeness of this of the monotone KW game of F. So first, given some function f, we have this natural rectangle cover, which is simply I just look at all the bits of my inputs, and whenever I look at all x's such that xi equals 1, all y such that yi equals 0, and that will give me one rectangle, and I do this for all I, so I'll have a total of n rectangles, and that covers all my inputs. So this would be a rectangle cover for the monotone KW game of F. So I do have that this complexity is bounded by log n. And the completeness comes from the fact that, so if I have any rectangle cover, I can reduce this to some monotone KW game for some function f. Okay. So I'll try to sketch this here. So I will define the function. So I'm given these rectangles, and I have to define this function, and I'll define it by, it's going to be a partial function, by defining the preimage of 1 and the preimage of 0. Okay. So for this, I'll consider all possible inputs for Alice of the problem, all possible U's. And so I will look at a U and consider all the rectangles that this U crosses when I vary the possible Bob inputs. So in this case, it's crossing R1 and R2, but not R3 and R4 for this U. So that would give me a string of 1, 1, 0, 0. So that this is what this function, I forgot what I want to call this. It's indicator for rectangles for U. Okay. And I'll do something similar for the V's, but I'll look at the opposite of the indicator. So now whenever it crosses, so here it's crossing all of them except for R2. So now I will have a 1 only in the second position. It has a 0 in all the rectangles it crosses. And you can sort of tell what I'm getting at, because exactly where they coincide, that rectangle is where Alice has a 1 and Bob has to have a 0 in all the rectangles that, well, in this rectangle, yeah, where they coincide. So first, let's argue that, okay, yeah, so the preimage of 1 will be, for I will just look at all u's and just look at all the strings I can get. And preimage of 0, I will look at all v's and all the strings I get by the non-indicator vector. So first, yeah, we have to argue that this is well defined, that this is actually a function, a partial function. So for any uv, there is some rectangle, since this is a total function, there is some rectangle where they're both in. And this corresponds exactly to some input where Alice has a 1 and Bob has a 0. So they cannot be giving the same string. So this is a well-defined function. And then from here, we can also see that if R1 is a possible answer, then bit 1 will also be a possible answer, and vice versa. If this bit 1 where they differ is a possible answer, that means that Alice is in rectangle 1 and Bob is in rectangle 1, because that's how we define it. This can be a little bit tricky, and I'm not sure I explained it so well, so please ask if it's not clear. Okay. Okay, so that in this sense, the monotone version is the one that is complete. We can't do the same thing for the non-monotone version. So we need this, it's harder, so it's easier to reduce things to it. So yeah, what I've tried to do, making the slides also similar, is to show that there's really like a strong parallel between these two worlds. So on one side, we had these basic like objects, which was these unsatisfiable CNF formulas. We defined a total search problem. And then we saw that, yeah, the tree-like resolution refutation was equivalent to the decision tree of these total search problems. And on the other side, we have these monotone Boolean functions. We have also a total search problem. And then we have this equivalence between monotone Boolean formulas and communication protocols for the monotone KW game. And we can also continue viewing this parallel. So these formulas, they are a bottom-up way of viewing the object. We're starting from the variables and building up the formula. And the communication protocols are a top-down, right? Alice and Bob are communicating. And the same thing here. We have a refutation is this bottom-up. From axioms, I have to derive contradiction. And the decision tree is a top-down view. And then here we have clauses for refutations. That's the objects in each node. And for the decision tree, we have partial assignments. And then we have these, yeah, deduction rules versus querying variables. And here we have for the circuit intermediate functions, and for the protocols, we have these rectangles. We have, yeah, gates versus the communicated bits. And we have these both canonical search problems. So there's a real like parallel we can see between both worlds.
But I mean, isn't the parallel true even for normal?
Sorry?
Isn't the parallel hold also for normal?
Except for this, yeah.
Except for the
The canonical, yeah. Yes. Yes, and then in both settings, we can also have a DAG-like version. So this is just normal resolution. And a decision DAG, I won't really define it, but you can think of, I can merge parts of the tree, which would actually look the same. That's the idea. So I can get something smaller. Yeah, because I don't have to repeat this. And then here I can also consider circuits, and there's also a same kind of merging idea that can be done for communication protocols, which creates something that we call rectangle DAGs. And we have the same kind of relation with regards to size here, size of circuits, size of these. Is that DAGs. So now, yeah, I'd like to talk about how these two worlds relate. So this interpolation and lifting. Are there any questions before I move on? Okay, so yeah, how can I turn a falsified cross search problem into a monotone KW game? Well, I need the game. I have two players, so I need to somehow partition the variables of my search problem into two sets. So I have my original variables. I can simply, I don't know, in some way partition it between Alice and Bob. I give some variables to Alice, some to Bob. And it's not hard to see that if I have an efficient decision tree for this problem, then I can easily get an efficient communication protocol for the same problem, but now with the variables partitioned. So whenever the decision tree queries some of the original variable Zi, whoever has that variable will simply tell the other player what the variable is, and they can just simulate the decision tree.
Search F not correspond to monotone KW. The search should be F, which is monotone itself, no? In some sense, or the set monotone.
So here I haven't gone into the monotone KW game. How that will come in is because it's canonical. Here I'm getting to sum. So that's this point here. So I'm getting to some total search problem. And now I want to get to a monotone KW game. And I will use exactly the fact that it's complete. So that's what allows me to actually get. And if we just had KW game, I can't guarantee that there would be such a translation. So let's see how this translation works. This is exactly where interpolation comes in. So this was, yeah, something already appearing in, this is Rasparov 90, but also that the Pavels have a more recent paper of 2017. And what they showed is that for any partition xy of the variables, this search problem with this partition variables is exactly equivalent to the monotone KW game for this function here. Okay, so before I get to this function, let me go back to something that Tony talked about when she talked about interpolation. She talked about these split formulas, right? So we have a formula that has some common variables, z, and part of the formula is saying that z is encoding a graph that has a k-click, and the other part is saying that z is encoding a graph that is k-1 colorable. And what the function that you get here would be the click coloring function. So it receives as input this graph, it outputs 1 if z has a k-click, 0 if z is k-1 colorable, and it can output anything if none are the case. And this is exactly what you can get by doing the correct partition of the variables here. So the idea is that the z will define, yeah, sorry, I didn't write this here. So every clause CI, this CIY is the part of CI that contains only the variables given to Bob. And CYX is the part of the clause that contains only the variables given to Alice. And the ZI is defining into which set I would like these the CI to go to. If they were both satisfiable, that would mean I would have a satisfying assignment for the whole formula. because yeah, it would be satisfying all the positions where zi equals 0, all the clauses where zi equals 0 by the x variables, and all the clauses where zi equals 1 by the y variables. So it can't be that they're both satisfiable. And here the goal is to actually determine which one is not satisfiable.
The original interpolation results by Karchmer, for instance. So it was not as you described that search reduces to monotone. It was a specific search for a specific error that has to be monotone. So he and Rathbone, they translated each proof line into a monotone communication protocol, and then it translates together into a monotone circuit. You're doing something more general.
Yeah, so this is just translating the problems themselves. This is not saying whether the proof system gets, so what they show is that given resolution, refutation, I can get a monotone circuit by translating each step, right? This I'm not doing here. Here I'm only talking about the problems that they're solving. It's a reduction between problems. So I guess the corresponding here would be that if I could compute this function, I would be interpolating this circuit, interpolating this formula. So it's just the relation between the problems.
Just questioning where does the supposedly modern change between the translation into just monotone, and you've shown that you say that it's for any f, it's going to be translatable into monotone lower bound. That's why.
For any formula f, I can. It's equivalent to the monotone of this function here.
Yes. This was not the case in the original.
Yeah, the original ones, it had to be like this split kind of formula, right? That's the difference, is that, yeah, here it had to be formulas that had these common variables. And
no, it was not enough there. It's not just the split. The split has to be monotone in the sense that the x.
if you want monotone interpolation, yes, yes.
So, yeah, okay.
This is giving you monotone interpolation. Maybe I should have said that. I'm sorry. So if I flip any bit of z from 0 to 1, that means I'm moving some pauses from here to here. So that means that the function can only change from 1 to 0. So yeah, this is a monotone function. Yeah, sorry, I should have. Okay, yeah, and I was going to mention that, so what's, Krajcek and then also Pudlak showed was that if, by using this known monotone circuit lower bound for this click coloring function, I would get a lower bound for resolution and then for cutting planes for this formula here. So this was their result. And using this more general translation, in two independent papers, they showed that you can get lower bounds for cutting planes for these random log n CNFs. And these are not these kind of split formulas, so you couldn't get it via this this view of interpolation. Okay. Right, and so what we have, like summarizing, so if we have a decision tree for the search problem F, then we have a communication protocol for the search problem with the partitioned variable, and that is equivalent to the monotone KW game of this function. So given a small decision tree or a small depth decision tree, I get a small depth communication protocol for this problem. And I can view this in terms of lower bound, which is usually how, I wrote here in terms of proof and circuits. And I can view this in terms of lower bounds. Proving a lower bound here gives me a lower bound here. And now I guess the question is, we said there's these two relations. So what about the converse, right? So we saw upper bounds for search F gives upper bounds for its monotone KW game. And it's not true that the other direction is always holds. But is it the case that at least for some formulas, the converse is also true? And this is exactly what we get from lifting. So if this formula is a lifted formula for a right gadget, then this is true. By lifted, what I mean, so a gadget is just a function which has a partitioned input, and I will just compose my original formula with n copies of this gadget, one for each input. So this gives a natural partition of the variables of the original function by what I have in the gadget, and I simply give all of one of the sides to Alice and the other side to Bob. So for the right gadget, this function that I get by composing will the converse will also hold. And this right gadget there are other gadgets that work depending on the lifting theorem, but the most general gadget is this indexing gadget, which is simply I have a string y of length L, and I have a pointer to somewhere in that string. And the indexing is simply I'll just look at the x position in the y string, and that's my function. And this is what the lifting theorem says. It's exactly the other direction. So if I have a size S step D communication protocol for that same function, then I get a poly S O of the decision tree for this composed function. And this is has been used to prove lower bounds. And it's somehow I feel like it's nicer because it's easier to prove lower bounds for decision trees than it is for communication protocols. So in some sense, I'm transferring the hard problem of proving a communication protocol or a circuit lower bound to an easier problem of considering decision trees. Okay, so this is the relation we saw for interpolation. This is the corresponding relation for lifting in the other direction, which here I just wrote it in terms of the lower bounds that we usually use. So it's a depth D decision tree lower bound would give a size n to the D communication protocol. And again, here I've been talking about trees, but this also works for DAGs. So I can have rectangle DAGs and decision DAGs. And then the difference is that instead of depth, I use the notion of width. That's the difference in the DAG world. So just to mention, we said from interpolation, we were able to get from monotone circuit lower bounds in proof complexity. And from this lifting, we can get from a resolution with lower bound, for example, for pigeonhole principle, we can get a monotone, which is something, I guess, easy to prove. We can get just black box by using this, a monotone circuit lower bound for the click coloring function. So it's, it gives you a black box way of getting monotone circuit lower bounds for some functions. Yeah. Yes.
Is there more general, like, do other gadgets functions work? Is there sort of a more general, if there are, is there more general characterizations for the properties that you need to make such a theorem go through?
So yeah, you can use other functions. So there's other monotone circuit lower bounds you can use by just same gadget indexing. You can get other lower bounds. With regards to other gadgets, there are some more general lifting theorems, but for the tree-like case. For the DAG-like, the only gadget that I know of is the indexing gadget, for which you could get lower bounds.
The diagonal lower bound. Oh, there's no proof system.
Oh, it's just resolution and monotone circuits. So this will correspond to resolution with lower bound, and here this would correspond to monotone circuits. And then just to mention some of the recent results that came from these lifting theorems. So one of them was 2 to the n lower bound for some monotone formulas, computing some function in NP. So this is not, this is a function in P, not in P. From function in monotone P, there's almost the optimal lower bound. And these were proved using lifting. Also, there was some separation proved in in the monotone bounded depth world, and also between monotone circuits and monotone and C2, or in C2, sorry, not monotone. And then also this result, lower bounds for cutting planes and monotone circuits from this with lower bound for resolution. So this is using the DAG-like lifting theorem, and and this was the only way we knew of proving cutting planes lower bound was via interpolation. So this gave like another way of proving cutting planes lower bounds. And this was this generalized interpolation that gave this random log n lower bounds for cutting planes. There have been some also size space trade-offs for different proof systems, also using lifting. And there are even some results which are not directly related to proof circuit complexity. So this is one I particularly like. It's very combinatorial, and it uses also this machinery to. Okay, so just to sum up, so this is part of a more general framework. So you can't see this very well, but we talked about the tree-like systems, this tree-like relations here. DAG-like relations would correspond to PLS. But there are other subclasses of TF and P which also have corresponding proof systems, some of which we also have a corresponding circuit model, but not for all of them. And one interesting problem that I've heard someone mention here, but is there so we have this generalized picture which we can view for decision trees and for communication complexity. And for some of these, we have lifting theorems relating the decision tree and the communication worlds. Can we prove a generalized, like from any class decision tree to any class communication, to the same class communication? If so, we could get lower bounds for communication classes, which we don't know because we only know the lower bounds for the query analog. So if there were such lifting theorems, we could get lower bounds. And then I think there are many interesting questions regarding these lifting theorems. What is their relation with other lower bound techniques? What can it prove? What can it not prove? And then there are, I think many questions, I guess, in proofs and circuit complexity of things that seem simple enough, but we don't know how to do. And can we also understand like why is this hard? Why can't we prove exponential size lower bound for monotone circuits for matching? Is there So one thing is matching, it does not seem to be a lifted type of function. So it seems like you can't prove definitely any exponential lower bound using lifting. But can we understand, like, yeah, can we give a good excuse why we haven't been able to prove this yet?
What is the best low bound for matching?
It's quasi-polynomial. Yeah, for monotone circuits. It has a linear depth lower bound, but nice. Okay, so thank you.
More questions for Susanna?
Just a clarification for, you've used, the lifting is not matched precisely with the monotone search problem of Rubich and Kudlak. Not the same, because for this, right, and I didn't succeed to follow when we use lifting and get some result. Just the reduction to from instead of split formulas to these monotones.
Like when you use interpolation, or no?
Well, what was the precise formalization of the lifting theorem? Wasn't it only applied to the case when you use the function?
Yeah, but for every search function, you have a function. So a curve and a gal result. Define the search problem. You can define a function for that.
Right.
So it will apply to some function.
But it was a specific one.
It was this function, the same one we had used before, but for the composed.
Why did you need to use the other search, the one from the monotone sect problem? A couple of slides before.
Yeah, or
No, before this. Oh, this one, yeah.
this one. Okay, yeah, this is for interpolation. So I was saying that we can automatically, we just split the variables and we get this search problem.
Oh, I see. Just for a specific case.
And then from here we can show its equivalence to some for some function, to the monotone KWK for that function.
Okay.
So you mentioned at the end resolution of parities.
Yes.
You have the same connection with parity decision trees like you have for resolution.
You have the same connection to parity decision trees for the tree-like version.
Yeah.
Yeah. Yes. Yes.
And for the DAG-like version.
For the DAG-like version, then you would have to define. I think you can define the DAG-like version of the. Yes.
Can you say something about what makes indexing a good gadget for lifting?
Okay, first it's universal. So any gadget that you have, you can simply on the Bob side, just write out all possible outputs you would get. And then Alice simply points to, so it's the hardest possible gadget.
I see.
So that's.
That also makes it too large.
In Bob's side, it is too large, that's true. But usually it's enough to have one small size. Side. So because Alice can simply send her pointer and Bob doesn't have to send anything except one bit. So even though he has a larger, input, okay. But it would be interesting to get something like more balanced and smaller gadgets. Yeah.
So then, yes, was that a question? Let's thank Susanna again. 30.